Today we will discuss valence shell electron pair repulsion theory in detail. And we will also discuss how this theory helps to draw the shape and geometry of molecules, just like examples. We will discuss all possible shapes and geometries of molecules on the basis of VSEPR theory in the next video. Before we start, like, share, and subscribe to Chemistry Spot for more videos. Let us suppose we have a water molecule. Its formula is H2O. Its central atom is oxygen. Oxygen has 6 valence electrons. It uses 2 electrons to form bonds with 2 hydrogen atoms. These pairs of electrons are called bond pairs of electrons. While the remaining 4 electrons of oxygen do not take part in bond formation, they pair up together to form 2 lone pairs of electrons. So, in a water molecule, there are 2 lone pairs and 2 bond pairs of electrons. According to VSEPR theory, these lone pairs and bond pairs of electrons decide the shape and geometry of any molecule. Due to similar charges, electron pairs repel each other and try to remain at the maximum distance. We start with an example of BCl2. In BCl2, beryllium is the central element. It has 2 valence electrons because it belongs to group 2 of the periodic table. It uses both valence electrons to form 2 bonds with 2 chlorine atoms. So, in the BCl2 molecule, there are 2 bond pairs and no lone pair. Due to similar charges, these 2 bond pairs of electrons repel each other and move far apart. As a result, the shape of the molecule becomes linear. Its geometry also becomes linear. Its bond angle becomes 180 degrees. So, according to VSEPR theory, electron pairs repel each other and try to remain at the maximum distance. Lone pairs repel more strongly than bond pairs. For example, ammonia. Its formula is NH3. In NH3, nitrogen is the central element. It has 5 valence electrons because it belongs to group 15 of the periodic table. It uses 3 valence electrons to form 3 bond pairs with 3 hydrogen atoms. The remaining 2 electrons pair up to form 1 lone pair. So, in the NH3 molecule, there are 3 bond pairs and 1 lone pair. All electron pairs repel each other. But lone pair repulsion is stronger than bond pair repulsion. Due to stronger repulsion, the lone pair pushes the bond pairs slightly closer together. As a result, the shape of the molecule becomes trigonal pyramidal. Its electron geometry becomes tetrahedral. Its bond angle unexpectedly becomes about 107 degrees. It is due to the greater repulsion of the lone pair-bond pair. So, according to VSEPR theory, lone pairs repel more strongly than bond pairs. The order of repulsion is lone pair repulsion is greater than lone pair-bond pair repulsion, and lone pair-bond pair repulsion is greater than bond pair-bond pair repulsion. The geometry and molecular shape of the same molecule may be the same or different. If a molecule has no lone pair, then it will have the same shape and geometry. For example, BCl2 has no lone pair of electrons. It has only 2 bond pairs. Its shape and geometry both are the same, meaning linear. But if a molecule contains any lone pair, its shape and geometry become different. For example, in the case of ammonia, there is a lone pair of electrons. So, its shape and geometry are different. Its shape is trigonal pyramidal and its geometry is tetrahedral. A double bond or triple bond is counted as a single region of electron density to determine the shape and geometry of a molecule. For example, in the case of carbon dioxide, there are 2 double bonds between carbon and oxygen. Its formula is CO2. Its shape and geometry are linear. But in the case of BCl2, there are 2 single bonds between beryllium and chlorine. Its shape and geometry are also linear. We will discuss all other possible shapes in the next video. Thanks for watching. Do not forget to like, share, and subscribe to Chemistry Spot.